Buonasera a tutti e siamo qui di nuovo con i giovedì di IEIT. Sono Paolo Ravazzani, il direttore dell'Istituto di Elettronica e di Ingegneria dell'Informazione e delle Telecomunicazioni del Consiglio Nazionale delle Ricerche e siamo qui per un nuovo appuntamento per affrontare la ricerca, l'innovazione, la visione del futuro nell'accademia, nell'industria. Stasera abbiamo l'onore di avere con noi il professor Massimo Mastrangeli della Delft University of Technology, a cui fra pochi secondi do la parola. Ci parlerà su un argomento veramente affascinante che sono gli organ on chip. Per cui lascio veramente la parola subito a Lucanos, che introdurrà il nostro ospite, che colgo l'occasione per ringraziare per la disponibilità. Quindi Lucanos, a te la parola.
Okay. Thank you, Paolo, very much for the floor, and it's a pleasure to me to have here my Professor Massimo Mastrangeli and opening this new series of the Tuesday seminars of our institution. I have the pleasure to know Massimo at the University of Pisa, where he has his bachelor and master degree. And at the moment, he is an associated professor of the Department of Microelectronics of the Delft University of Technology. And his currently research is focused on design and fabrication of innovative silicon polymer-based electro-mechanical organ-on-chip devices and alternative processes for ultra-high throughput assembly of microcomponents. Now, I don't want to take up too much of the speaker's time, and so I give you the floor, Massimo, and thank you again for your availability.
Thank you very much, Lucanus. It's really a pleasure to be here. We had the opportunity to talk to you and to all the audience. I would like also to thank Dr. Ravazzani for the kind words, kind introduction. And indeed, as you mentioned, Lucanus, for me, everything started in Pisa, indeed, and for this I am certainly very thankful. And if you allow me today, I try to give you back a little bit of what I received in the years there. In fact, with Lucanus, we met almost exactly 20 years ago. In the break, I was thinking of that, Lucanus, when I was inquiring for a master thesis that indeed I then developed between 2004 2005 in the department. Today, I would like to show you, in a nutshell, the work that we have been conducting in the past few years on organs on chip, and particularly a perspective that we are shaping with my group here in Delft to use micro-electro-mechanical systems to develop this type of research. Again, everything that I will show may be quite familiar and as far as the topic to some of you, but if you allow me, I also will start with a rather more general justification of why organ on chip technology is timely, is possible, first of all, and where it may lead, also maybe partly thanks to our contributions. I would also like to add that indeed the journey from, say, Pisa, on a more personal note, to here was not straight. And during the journey, I had the opportunity to work on other aspects of the electronics and gradually moved a bit further into materials, into even a bit of soft robotics. And then once I joined Delft, it's about 6 years ago, I could put everything together in a way and use it to develop such a very fascinating research. In a nutshell, what I like to tell you about in a few minutes is, first of all, as I mentioned, the origin of organ on chip technology and what it can achieve, why it's timely to develop such technology. I will then focus on our approach on organs on chip, where we believe MEMS technology is really purposefully dedicated to provide actuation and sensing for tissues and generally for in vitro cultures, as I will explain, and conclude with a perspective that encompasses the combination of organ-on-chip devices into what we call platforms. Also, and particularly to provide also a direction for standardizing such technology. Of course, standardization and research may seem a bit of, at the opposite side of the spectrum, but I hope that I will give you also an idea of how they can conveniently coexist. And I'm certainly open for questions meanwhile, and I guess that at the end anyway, we will have time to eventually discuss directly. To give a context, I've always tend to start with reminding of what the drug development process is nowadays. The procedure of the development and eventual acceptance of drugs from the initial solution space till adoption passes through several stages. And from the very large initial library of biochemical compounds that are supposed candidates for a certain application, and gradually is the space of solution is being refined through different stages, first preclinical and then clinical, until eventually at least one candidate makes to the approval through the regulators and eventually enters the market. It's a sort of sieve. It's a filter for solutions. And it's has proved to work to a fair extent, but it's probably not the best that we can develop at the time. And even if it works, there are many aspects that can be eventually made more efficient and powerful. And this may have some significant societal consequences. In particular, the cost and the time that the process takes are sort of an issue. And to give you a more of insight, I take this picture from the work of Lova that gives you an idea of the efforts and the time that it takes to go through the process. On average, for what the sources that we have available, the process takes about 10 years, with a compound cost, including also particularly the failures in the developments, of about $2 billion, or say euros, more or less, per compound. So certainly, I don't think we are here advocating such costs or particularly speaking for the pharma, but it's certainly a load. And imagine this is anyway only for a single eventually compound. Now, along the trajectory of the development of drugs and therapies, several test cases or test benches, so to say, are used. We know that in the preclinical phase, in vitro cell cultures and also animals are used. Animals are being phased out, and particularly for the cosmetics, they are already banned, at least in the European Union. And as then the candidates enter the clinics, larger and larger cohorts of volunteers are used. The process indeed is phased because also of particular requirements on the quality control on the drugs. And partly this is also the reason why the throughput of the entire process is not great. Here, in fact, recent data highlights the decrease in throughput of basically the number of drugs that makes to the market per cost of development across the recent decades. You see that the trend is not impressive and it's negative. You particularly look also at the logarithmic scale on the vertical axis. You see there was a certain rebound in the recent years, but it's not for say technological reasons mainly. And so since we are, I guess, largely into electronic audience, this may look for your eyes, for some of you, as the inverse of something that you are more accustomed to. Which is, as we know, the Moore's law for the exponential growth of throughput in terms of computational power, generally speaking, for electronic components. So this kind of disparity in this has given the reason for some people to call this reduced throughput in drug development the inverse Moore's law, so-called Aron's law. And even if suppose that the drugs makes it to the market, does it work? How effective it is? Well, if you want to look in the literature and the available data, the situation is good but not great. the efficacy is in fact not as high as one could expect. Probably we talk about, in a good case, 1 to 3 successful transfer from the preclinical to the clinical and eventually to the final adoption case. And this largely depends on the type of pathologies and the particular cases. So the situation generally is not fluid, is good, and indeed quality controls particularly is imposing a large quality of the results, but certainly there is an ample margin of improvement. So what can be done? Of course, I try to raise also some drama so that I can show you some some solutions. In a way, the approach that organ-on-chip proposes is to recreate a microenvironment similar to the one that tissues and organs find in the human body in vivo, outside of the body itself. In the words of Lorna Ewart, a home for cells or tissues away from home. And this, in a nutshell, what ideally one would imagine as having a sort of sorry. Recapitulation of in vivo physiology, but in an in vitro condition. And this is also the aim of organ-on-chip technology. And there is a very beautiful and powerful convergence that can lead to this type of achievement. It's a very beautiful convergence because it entails the capacity of technology that we master. Sorry, 1 second. Excuse me for this. On one side, the convergence of micro-mechanical systems and technology, and the other side, just the constitution of basically a vast majority of our organs. Let's start for the first. It's interesting to note that for evolutionary reasons, the physiology of a large part of our organs and tissues is largely redundant. Many of our organs are composed by multiple hundreds of replicas of the same fundamental unit that we can call organoid or physiological organoid. For instance, here I show you some of the examples. For instance, the liver is composed by multiple lobuli, or in the lung, there are the alveoli as the organoids, and so on. This is interesting. It means that if one wants to replicate in a small scale the physiology or pathophysiology of an organ, it doesn't need to take the entire organ. It can take at least one of such units. And it's interesting that the dimension of such units is in the millimetric or sub-millimetric scale range. It's very interesting because, as we know, in parallel to the recent development in tissue engineering, we have been developing, we as the human species, let's say, have been developing MEMS, micro-mechanical systems that, as you may well know, use to a large extent the same technology that was developed to first fabricate integrated circuits to fabricate three-dimensional micro-mechanical structure generally, and generally sensors and actuators. Here I show a famous example. I'm also fond of this example because it reminds me again of the times that I was following the course of MEMS for the first time there in Pisa. And at the time, it was still advertised as the most complicated machine that was made by men. And it's the DLP, the digital light projector chip made originally by Texas Instruments. And again, here it's I propose it to emphasize that this is an actuator eventually, modulating the direction of lights with MEMS on top of a CMOS substrate, and the size at which the operations happens, and the size of each pixel, each micromirror, is indeed also in the order of tens or hundreds of microns. So there is an inherent convergence of scale between the organoids and what MEMS can do, and there is also functional convergence. Because in fact, to make a realistic cell culture environment outside of the body, the cells and the tissues still need to receive the same or very similar stimuli that they receive in the in vivo condition. And these amount to largely mechanical and electrical stimulation. And so This justifies what I tend to like to call the biotechnological convergence that underlies organ-on-chip. On one side, again, cell and tissue engineering, supported by revolutionary achievements in genetics, and on the other side, indeed, the technological component, starting with MEMS and then adding to the flavors of microfluidics. Here in the center, I show you, by the way, an example of what our interpretation of organ-on-chip looks like. This is a chip, as you see, composed by a microfluidic tripartite channel on top of a transparent window inside a silicon frame. And this is the product of a spin-off of our group called Beyond, here, based still in Delft. So I hope this offers you an introduction to the role and the timeliness of organ-on-chip technology. And I will try now to give you some examples of opportunities and the implementation of such technology based on our research. And since I indeed started being directly involved in organ-on-chip research, I tried to organize the 4 main directions of research. I will talk about 3 of them, given the time. And again, to highlight the opportunities, the different scenarios that one can face, and where a micromechanical system, micro-electro-mechanical system can play a role. I will start with engineer hard tissue structures that emphasize the geometrical topographical aspect. Here I show you the concept of what we have been developing in this respect. Imagine a situation, a geometry that allows to develop cardiac tissues. This is what you see in this picture. The structure is actually very simple. It's composed by an elastomeric substrate, composed by polydimethylsiloxane, PDMS in short. And at the center, if you see, and particularly if I can use the pointer here, you see the 2 vertical pillars that are extruding from the substrate and are surrounded by a micro well, an elliptical well that will confine the medium and the cells seeded into the plate. And all of this is contained into a larger well. Now, the reason of using the pillars is that they will provide anchors for the bundles of cardiomyocytes and fibroblasts to self-organize and form indeed an organized structure that will show the phenotypes, the functionality of the cardiac tissues. Fabrication-wise, the structure is basic, and in fact is an example of the most common approach so far in microfluidics, and particularly in lab-on-chip and in organ-on-chip, which is essentially soft lithography. Fabrication is, we work always at, when we can, at wafer scale. So we produce batches of nominally identical devices. And the fabrication is here highlighted very simply. We use a silicon as a substrate. We etch by deep reactive ion etching trenches to create the mold, the negative of the final structure. We cast PDMS into the mold and then peel it off. So very simply, a one-step fabrication, if you like. And it's important for us then to know the mechanical properties of the pillars in particular, and we do that by non-indentation. And here's an example of what we mean by wafer scale fabrication. This is the work by my ex-PhD student, now turned postdoc, Milica Dostanic. She was fabricating the structure and then manually moving them at the bottom of an anti-6 well plate that you see here in the top right. And then these devices were transferred to our biology collaborators. By now, Melissa, she can do the cell cultures herself. A combination of cardiomyocytes, fibroblasts, and medium was seeded into the wells. And as you can see here in the time lapse, in a matter of a few hours and a few days, the aggregate self-organizes into a bundle that hangs on the pillars. And since we are talking about cardiomyocytes, so cells that are spontaneously producing voltage in their electromechanical indeed motion, this structure eventually starts to beat in the best case, of course. And now we can use the deflection that the beating of the tissues imposes on the pillar to reconstruct the dynamics of the motion, of the contractile dynamics of the tissues. This is typically done by optically tracking the motion of the tips of the pillar. And by the way, this is why also it is important for us to know the mechanical properties of the material itself and technically the elastic constant of the cantilevers, because this information together with the deflection of the tips allows us to calculate the force that also the tissues apply with a certain margin of uncertainty that I will mention in a second. If the tracking works well, this is the typical data that one can extract from such a device. It looks like a sort of ECG of the heart modification. In fact, Milica and collaborators have also developed an open software to automatize, to an extent, the extraction of such data. I mentioned that we have certain uncertainty still in the estimation of the force that the tissue apply, and this is due to the uncertainty in the vertical localization of the tissue around the pillar, assuming that the pillar is fully straight, which was the original condition that we were asked to work with by our biologists. But later on, we were able to convince them that with a simple modification of the geometry of the pillars, this problem could be largely addressed. What we did, indeed, we fabricated a mold in silicon that imposes a taper geometry to the pillars. This, you can see here on the top right again. The kink, the tapering at the center, in this case of the pillars, is enough to localize during their growth and the assembly the vertical position of the bundle. And knowing this to a much better accuracy allows us to reduce largely the dispersion of the force measurements, so much that we believe by now, and I think by now Milica has gathered many more supporting evidence, the variety, that the dispersion of the data is largely the one inherent in the biology of the tissue themselves. Now, this is still about the basic structure with some mechanical variation, geometrical variation. Being engineers, electronic engineers in particular, we could not refrain to integrate additional functionality. And in fact, we did two types of additions. One was to integrate beside the elastic pillars, electrodes, in this case in titanium nitride, to provide pacing to the tissues. Just like a pacemaker supports and forces the activity of the heart in vivo, similarly, in vitro cultures for cardiomyocytes, is known by now that forcing the contraction of the tissues helps their maturation. I also want to mention in this case that most of the biology provided by our colleagues that I will show in these slides is based on human-induced pluripotent stem cells. This is particularly the case for the cardiomyocytes used in this study. So forcing the contraction helps the maturation, particularly of the stem cells, which in other words is also something that fundamentally is beneficial from organs on chip. Since you may know that the development of a mature phenotype in the cardiomyocytes and generally in stem cells is still something of an issue in that field. And Milica then was able also to turn this system into a multi-well plate format to increase the throughput of the assay. Conversely, we also wanted to at least conceive a way to measure the deformation of the pillars and indirectly the dynamics of the tissue electrically. And what we found out, we wanted to try at least, was a capacitive readout. The idea that we implemented was to have a coplanar capacitive sensor embedded inside the substrate in correspondence of the intersection with the pillars themselves. So just beneath the pillars themselves. If you see my cursor basically around this area here. The reason being that since we mold the entire structure of the pillars and the substrate, the deformation of the pillars is also introduced into the substrate. And we place a sensor in the region that is mostly deformed by such pillar bending. And the deformation will also deform the distance between the arms of the capacitor, and from that we derive a change in capacitance, which we correlate with the force applied on the tissues. We are still not at the stage of testing this sensor with the actual biology, but we did test them mechanically by poking with a nano-indenter on a single pillar and measuring in real time the change in base capacitance that we induce. And the results that you see here, which are the work of 2 master students, seem encouraging. Now, hopefully, in the next available occasion, I may be able also to tell you what happens with the actual tissues, but I hope this also provides already a nice proof of concept. So much for the engineered tissues, or for art on chip in general. I want to show you now another direction of research that deals with the brain, or brain on chip, so to say. The brain is admittedly probably the most complex organ we have, and is certainly the one that relies on three-dimensional organization particularly. And so when recording electrical activity, just like cardiomyocytes brain, the neurons, as we know, are electrogenic, that generate field potential. Recording the activity is typically done by using by now well-established systems that we call multi-electrode or micro-electrode arrays, just like the one that I show you in the slide. These are very well-established systems that record tens or even by now thousands of signals from electrodes typically distributed on a plane, a two-dimensional array. However, as I mentioned, the brain is not two-dimensional really, so there is a lot of interest in to go into the third dimension. And the first approach to go 3D is to have indetermination not confined to the plane, but extruding from it. And as you see in the top left image, three-dimensional electrodes have the shape of such termination to eventually protrude inside the surface of the tissues. However, talking to biologists, at least our colleagues, it turns out that it may be even more interesting to really record from a matrix of electrodes distributed in space. So to be able to track the electrical activity in the neural networks in full three-dimensional space. And so we try to go along this idea, and again, working, at least starting with silicon, the starting idea we had was to fabricate by anisotropic etching silicon micropyramids, and very boldly pattern by lithography electrodes on top of the pyramids, right? That's something easy to say, challenging to do, but we had the pleasure to have great PhD students that took up the challenge. And here I show you the results that were achieved by Nele Levin. You see here essentially the result of the process. Again, anisotropic etching of the silicon using TMAH, using an art mask of silicon nitride, and then indeed lithography on the slopes of such micropyramids, which were by design 100 micron tall. For whose patterning, certainly then we had to use a spray coating. Here is how the wafer looks like upon completion of most of the steps. And as I mentioned, this is an example of batch processing. In this case, it realized 12 chips per wafer. But as you can imagine, if I only give you silicon, you may be impressed. You may look at it, it's very shiny, but you cannot do much. So we still have to package it into a form that is convenient for our colleagues. And here is the process that we follow. On the left, on the right, you see a close-in picture of 3 electrodes, distinct electrodes, different heights and position along a single micropyramid. The array is composed by 20 of these micropyramids, and so for a total of 60 electrodes. And 60 is a magic number because it's the number of electrodes in a standard format for a multi-electrode array, single well. And so we finalize the chip by wire bonding to a PCB and protecting the wire bonds and forming a sort of well in the center for hosting the cell culture. So that's the outlook is really similar to, as I mentioned, a commercial MIA. And it was our intention to just give this to biologists just by the look of the outline of such chip would be already primed, would be already knowing what to do, what to use this chip for. And this is another view of the chip that we packaged. And we also were able to test preliminarily the performance of such chip using monolayers of cortical neurons, which seem to be indeed promising. As you see here, the readout from the entire array of pyramids, and also a zoom in into an example of firing of an electron. And we are still interested in testing them further, particularly as for the purpose with thicker tissues that can really make use of the entire array, and eventually show that the pyramids may eventually enter beyond the surface of the tissues. The last device that I want to show you is perhaps the most complex that we have fabricated, and it's on the other hand, the purpose of the device is sensing, particularly electrochemical sensing. The electrochemical, or mainly the chemical properties of the culture environment, are critical, of course, for the well-being, for the health, and for the long-term viability of cell cultures. And on top of the list, there are typical pH, oxygen, and the concentration of various other species. So to start in this direction with the Hande, we wanted to introduce a charge sensor that later we tuned into a pH sensor based on field effect transistors. This may remind most of you of the ion sensitive and the field effect transistors that are 54 years old. And they, by the way, I discovered recently, were discovered in the University of Twente, which is still in the Netherlands. What we wanted to do specifically in this version was to combine the silicon-based FET, indeed, with a transparent and soft culturing area. And so we ended up conceiving the device composed by a frame of silicon, whereby the field effect transistors are fabricated with a central area that is composed by a suspended layer, a membrane of PDMS, which embeds the extension electrodes connected to the gate of the FETs. So in other words, the culture area is suspended onto the electrodes, and the charge in proximity of the tip of the electrodes is transferred to the gate of the FETs. And so this modulates the drain current, since it modulates the voltage prior to the gate. And so by monitoring the change in the drain current, we could monitor the relative change in the concentration of charge in proximity of the extension electrodes. This is how the chip looks like. You can recognize in the center the transparent window in PDMS, and in this case 8 electrodes, each connected to a separate, there are actually 4 NMOS and 4 PMOS on the silicon frame. The chip is 1 by 1 square centimeters in size. And again, in this case, we were able to fabricate up to 52 chips per wafer. We work still on 4-inch wafers, by the way. The process is rather long. It formally, I think, contains 155 steps, if one includes also the cleaning steps. And well, it proceeds anyway along ways that you can anticipate. There is a full BiCMOS 5-mask process to define the field effect transistors. And the exotic part is indeed the way in which we are able to integrate into the process PDMS as a structural layer in the last part of the processing, and particularly ensure that the electrodes, in this case either in titanium nitride again or also in aluminum, are still adherent sufficiently to the PDMS, which you may know is typically an issue. We have the knowledge that I can detail later if you want on how this can be achieved. At least we have a solution for that. And finally, we've packaged the system in a similar way as I shown before. We still connect to a common architecture for the readout for the output electrodes. And testing shows that indeed the devices do work as they should, as you can see from the output current of the ID versus VDS. And we tested the device with labeled solutions of known pH. And you can see that indeed we can discriminate between, in this case, large differences in pH, but we also, I don't show the data here, we can resolve up to 0.1 pH values for labeled solutions. We also tested the biocompatibility of the devices. Here you see some beautiful pictures that were taken by our colleagues from the Brain on Chip group, the Leiden University Medical Center, here close by. And again, we are now eager to test them to combine the cultures with real-time pH measurements in culture. Now, I would like to, in the remaining perhaps 10 minutes to address another topic, as I mentioned at the beginning, which gives perhaps also a longer-term perspective of the research. By the way, in our group, we are also in the process of developing additional devices, and eventually we can talk about that later on or in other occasions. But here, I think it's the opportunity to mention what in the field we feel as a sort of dilemma. It has to do, as I hinted at the beginning, with the dialectic between, on one side, exploration of the space of solutions, so the architectures that the devices can have and the functionality, and at the other side, the will to put order in such space in the variety of devices that have been reported in literature and even become commercial so far in the last roughly 2 decades. So the two things are a bit at odds. On one side, in other words, you have what we call the fit for purpose. So taking care of the functionality of each device specific typically for an organ. In fact, by now it's kind of wisdom in the field that there is no such device that can fit the entire variety or the entire diversity of tissues and organs. In this sense, we call the devices fit for purpose. By the way, also for validation or qualification and regulation of devices, the purpose of each device has to be declared upfront. On the other hand, indeed, we are aware that some sort of alignments and synchronization, in other words, standardization, is probably still beneficial. There have been cases, many cases, in fact, in the past of technology that were advertised and eventually hyped that missed perhaps a particular early stage such synchronization, such standardization. And I'm thinking, for instance, of microfluidics itself, which still lacks to a good extent important standards. And so in the process, there have been recommendations, even at European level, to introduce in some important aspects, some aspect of standardization. In particular, there is, since a few years, it has been established as a society, the European Organ on Chip Society, that coordinates the activity of organs on chip in Europe and also supervises the implementation of the European Organ on Chip roadmap for development. And in the roadmap, their recommendation to have organ on chip platforms has been introduced. The concept of a platform is actually inspired by examples in electronics. And in fact, what I'm going to tell you is part of a project that concluded last September that was called Move for Medical, whose mission was really to bring into the electronic medical device domain the success stories or the approach that was taken in electronics and that allows us to interface devices so beautifully because of indeed the introduction of standards. The Move for Medical project indeed contained several tracks, and one of them was dedicated to organs on chip, and I had the honor and the responsibility of leading that track. And here I would like to simplify what I've been saying about standardization of device in organ on chip by introducing the concept of the smart multi-well plate. The idea behind this approach is to use one of the few existing standards in microfluidics and particularly in, say, tissue engineering, which is the multi-well plate, and infuse it with the power of organ-on-chip technology. So here you see, with credits to Sandro Meucci from Micronit, the concept behind the plate. You can recognize probably 4 layers. On the top, the tidal plate, which gives the multi-well aspect to the device. And beneath, we introduce a microfluidic distribution layer, a layer for the organ-on-chip devices proper, and an electric distribution layer. In other words, we embed behind or beneath the tidal plate organ-on-chip devices which are perfusible and whose perfusion is achieved through connection by means of a microfluidic distribution layer, so a set of closed-loop fluidic circuits, and where the perfusion, so that the fluid flow, is driven by integrated micropumps. And the driving of the pumps, and as well as other electrical functionalities of the devices, is taken care by the electric distribution layer, which has the form of a printed circuit board, which is the very bottomest layer. You can also notice on the left side another block, and that's in the current implementation corresponds to a metal shielding of a stack of PCBs that are part of the electronic routing and the infrastructure of the plate. And that part is, by the way, reusable. So it's only the rest of the plate that is disposable. Disposability is indeed inherent in multi-well plates at this point. And the electronics, which is also the most expensive part of the plates, can be reused. I mentioned several features of this plate, and you see here on the top right the implementation, in fact, that we achieved across 3 years of project. And let me go a bit more into the details. As I mentioned, there are closed loops in the beneath the tidal plate. At this point, there are 16 of them, and each of them is dedicated to support one organ-on-chip device. And in each loop, a micropump is included. The micropump is a piezoelectric micropump, silicon-based and driven by a piezoelectric membrane. So unfortunately, it requires high voltage, and that's also a reason for having such embedded electronics into the plate. And I'll show you some other aspects. This is the injection molded distribution layer for the fluidic side. And you see the locations where the devices and the pumps can be attached to. And here is a picture of the micropump. The micropump at this point is fabricated by Fraunhofer EMFT, which is based in Munich, Germany. It's a beautiful, extremely compact device with 2 electrical contacts. And as far as organ-on-chip requirements for perfusion of tissues, it's beautiful. It covers a very big range of flow rates from very low ones to up to hundreds of microliters per minute. So it serves most of the requirements. And unfortunately, it also requires high voltage driving, but something that perhaps can be ameliorated in the future. And here is a schematic of how that's supposed to work. The membrane moves around the fluid, and from a sinusoidal motion of the membrane, the rectification of the flow is achieved by having check valves that open and close respectively during half of the cycles. And we tested, by the way, also the power that is generated by such a device, and we in fact noted that the power developed doesn't rise the temperature of the fluid dramatically. It should be noted that the actual use of cell cultures happens, in fact, inside dedicated environments called incubators that preserve conditions that are indeed similar to the human physiology. So very high humidity, almost 100% humidity, and controlled CO2 concentration and 37 degrees temperatures. The temperature increase due to the use of the pump is only minor, a fraction of degree, so it should be well compatible with the existence of cell cultures. And here I would like to stress the importance of standards, if you allow me. The way in which we try to propose this device as a prototype for including standardization is by prescribing only, beside the footprint and the pitch of the wells in the multi-well plate format, is prescribing the size and the location of the interconnects for each organ-on-chip device. In other words, any producer of organ-on-chip devices, just like us or multi-channel systems or any other company, interested in having a multi-well plate tailored to their application can well do it, as long as the device themselves comply with very simple geometrical rules, here schematized. Again, is the pitch and the distance with respect to the edges of the interconnects, particularly the fluidic ones. For the electrical interconnects, discussion is still ongoing, as well as the size. In the current implementation, the devices are 1 by 1 square centimeters. In the next implementation, they will be 0.75 by 0.75 millimeters squares. The reason being that this will allow integration of more than one organ-on-chip device into the same fluidic loop, and so open the perspective of multi-organ-on-chip on board. To test this functionality and prove that standardization gives benefits, in the project we had 3 companies, multi-channel systems, Beyond Chip and Beyond, multi-channel system from Germany, Beyond Chip from Spain, and Beyond from Netherlands, to optimize their existing devices to the multi-well plate. Multi-channel system developed a multi-retro array, as we can expect. Beyond Chip developed a transwell type full polymeric, full transparent device. Beyond developed an art-on-chip device similar to the one that I showed you at the beginning with the vertical pillars and a combination of polymer and silicon to be implemented into the plate. A look at the electrical distribution layer, the PCB, gives such an intricate pattern. It was the work of our lab manager, Filip Szczęjanowski. And in particular, we had to develop a 4-layer PCB. You see here the cutouts to allow the integration of the micro pump, the small one, and the organ-on-chip devices. The reason for this is that optical access, so the ability for biologists to look optically at the devices, and particularly at the core devices, needs to be preserved. It's expected that although we are developing electrical sensors, as we do, the optical inspection will remain primary, or at least very important for biologists. So all these devices are born with the requirement of ensuring full optical transparency across, and this is the reason, additional reason for having the cutouts in the PCBs. Here is the backside of the plate, and here is the conjunction of the PCB with the electrical with the fluidic distribution layer. This is the top view of the version of the plate that was developed for the devices by a multi-channel system. If you look indeed at this row where my pointer is, you will recognize the big reference electrodes that were part of the devices from multi-channel systems. You didn't miss to notice that this device doesn't have any tubings. Even if it's a microfluidic device, it doesn't have tubes for input and output of fluids. This is because we have micropumps embedded, as I mentioned, and it's really something we are proud of. However, we still need some power to be delivered to the plate. And the way we do that is by using a so-called docking station that you see here represented. The docking station itself allows 4 of the plates to be connected at the same time. And as you see, it contains additional electronics to connect via an inductive coupling to each of the plates. And both provide input and extract readout of the signals that can be then displayed onto a PC, for instance. You see here how the docking station can be stacked and eventually put into the incubator. And by the way, the reason of having the shield that you see here on the electronics is exactly to prevent the electronics from being disrupted by the incubator environment. And once you see an example of the exemplify, you are going to hinge it on one of the slots on the plate and on the station, and you are ready to enter the incubator. In the course of the project, we develop pick-and-place approaches to automate the assembly of the devices, particularly developed by Micronet here in the Netherlands, which is particularly important for fragile devices, just like the micropumps. And finally, the test of the functionality of the devices was accomplished both by all the three partners. Particularly, I showed the results for the chips of Beyond in the utilization of a channel and the cultivation of cardiomyocytes in their main well, as well as cultivation of skin tissues in the device by Beyond chip. With this, I hope that I have been faithful to the timing. I would like to conclude just by mentioning that I hope I gave you an example of and a good idea of what the electrical side or the electromechanical technology that we have been developing the last decades can be very useful for ground-chip devices. That the smart multiwire plate and generally these approaches that we call platforms can combine freedom of research and fit for purpose with interfacing and ease of use and the organization of the landscape. And finally, let me add another interesting aspect. It's certainly obvious for anybody that conducts similar research that success is particularly assured or actually may require necessarily interaction between academia and industry, and even more fundamentally, the very good understanding and communication between, let's say, engineers and technologists on one side and biologists or biotechnologists on the other side, which passes largely through the establishment and common understanding of a common language. There will be follow-up projects on the works that I've been showing you, and maybe in next occasion I will be able to tell you more about those. With that, I need to certainly acknowledge the beautiful work of many of the collaborators in the Morphomedical project across Europe, as well as my more direct collaborators here in the Netherlands. And I'd like to thank you for your attention today.
Thank you very much, Massimo, for very, very, very nice and impressive presentation and talk. And okay, so we have now a few minutes, 10 to up more minutes for question and curiosity. If you have someone, I saw Maurizio. Do you have some question for Massimo? Okay, you have the floor.
Okay, Massimo, nice to meet you. I am Maurizio. I have two quick questions. The first one is about the first example with the micropillars in PDMS for cardiomyocyte. I was wondering, do you use or everybody uses PDMS for historical reason, or because, for example, is it possible to do the same with the 3D printing with bioresin, for example, or there are some, for example, mechanical issue about the flexibility of the pillar? This is the first one. And the second one, I tell you immediately, then I can repeat, about the integrated ion sensor. How much is the fabrication cost for that? And how much is the scalability?
Yeah. Thank you, Maurizio. Nice to meet you as well. And the very interesting questions. Both of them are very relevant. So the first one, very interesting point. PDMS is probably the biggest reason why microfluidics has become popular. It's easy to process, widely available. So there is certainly a long legacy in the reason why we tend to use still PDMS, in spite of the fact that, for instance, its scalability, meaning its integration in production pilot lines, is certainly not feasible, not convenient. So for that, you would like to go for injection molding or other type of convenient process, whereby PDMS, for what we have seen, is not convenient. On the other hand, PDMS is a beautiful material for many aspects. For instance, oxygen transparent, so you don't need to perfuse your system for gases. It's kind of automatic. Transparent, biocompatible, not too expensive. It has a big defect. It's not unique to PDMS. It's for most hydrophobic polymers. Its hydrophobicity makes it a sponge for molecules, particularly for drugs. if they are hydrophobic, and this is not selective. So this is a knowledge that an issue. Some people, some groups are able to model this type of absorption of molecule, but generally that's not easy, and it's not convenient because when you are eventually going to use your model to expose to drugs, you want to know exactly what is the dose you inject in the tissue, and if you don't know what goes around, it's not good. But to answer to your point, 3D printing is a very good approach, especially, I would say, of course, you need to take care of the resolution, but particularly if you can also use it to implement additional materials or different materials that are, they in principle need to have similar properties, the good properties, and avoid this absorption issue. So certainly that's very interesting, and perhaps it can be to an extent scaled up. For the scaling up, to the other question, the process that we do, as I showed, is done on 10 centimeter 4-inch wafers, and we didn't even try to scale up larger. However, we have the impression that this could be probably easily done. We cannot easily estimate the cost. Probably if I did, I would be scared. But the approach we have is that, again, we don't use any specific, if you like, technology or tool, and exotic. The exotic part is the use of PDMS as a structural layer. But if you think, for instance, consider only the fat part, there is no reason why this could not be scaled to larger substrates. It's, for instance, 8-inch, as it's more or less becoming the norm. And this would then make obviously the chips much cheaper.
Yeah, and sorry, the last one, not politically correct question. You mentioned in the first slides Lorna and Emulate. I would like to have your honest opinion on that company, if you can, Massimo.
Yeah, maybe we do it. No, I'm kidding. We can stop the recording. I'm kidding.
Okay.
No. It's so indeed you recognize Emulate. Lorna was before that, as you may also know, in AstraZeneca, and I actually got in contact with her when I was conducting interviews to have a snapshot of the landscape in organs and chip, and then she moved to Emulate. Emulate is the first company that I think that, well, it's certainly the most famous company as far as organs and chip, a spin-off from the VC Institute in Boston, Massachusetts, and still probably the most visible company, which was actually very good because they probably were the first to raise really attention, visibility to the field generally, and were also able to raise a lot of money. They had good trials and connections with the FDA and the NIH and other institutes. On the other hand, now this is, take it with a pinch of salt, as we say, and that's certainly a part of the experience I had, maybe not correct. Their approach is not very compatible with standardization, for instance, because as far as I understand from collaborators, it's not easy to use their devices. In fact, they are selling the devices and all the suite of incubators and devices that you need to run them. But particularly, they are focusing on service. So in a way, it seems to me they are more asking customers to let them use in-house the devices to develop models. Admittedly, probably their models are very good. They do have great publication with some physiological relevance. However, their approach is a bit at odds. And beside the devices, which are, well, didn't have a slide on them, this big probably, and full in PDMS and fabricated manually, they are very expensive.
Yes.
Thank you very much.
I hope this is what that you.
Fantastic. Great. Thank you, Massimo.
Now I know Lorna will call me now and said.
Okay. So we can move to the second question from. Okay, you have the floor.
Sara Meneghello, I'm Silvia Scaglione. I'm using
Yeah. I know. I see. I read another name, but I don't. Okay.
Great talk, just a short question. So it's pretty intuitive, the great importance of electric stimulation when you have electrically active cells like cardiomyocytes and brain-related cells, as you mentioned. Can you comment from your experience about the importance of these electric stimulations and inputs or output, even when you use cells that are not electrically active?
Very interesting point. Nice to meet you as well, Sylvia, not Sarah.
Yeah.
Sure, indeed. Only a set of organs seems to be electrogenic, or at least responsive to directly, let's say, responsive to electrical stimulation. Heart and brain, most known. This as far as stimulation. It's probably true that some electrical background or electrical stimulation may induce development of cells. What is certainly true is that we use actually electrical input not directly to stimulate but to sense. I didn't show it here, but for instance, when one deals with tissue barriers, the blood-brain barrier, the gut, the skin, and others, a typical way to measure or quantify to an extent the performance is by, brutally said, passing current through the tissue and recording how much it comes out as a function of the frequency of the stimulation. This at DC, this is called endothelial electrical resistance, TER, and in terms of frequency, you can call it impedance spectroscopy. It gives an idea of how tight, for instance, are the junctions between the cells, and instead if there is gaps in between. As well as we are now talking about electrical, certainly if you can then also induce a transduction, so it's still provide an electrical input, but then locally transduce into, for instance, an acoustic field, there is even much more. For instance, with ultrasound use, you can stimulate or induce a reaction in basically all tissues, but particularly, for instance, you can activate ion channels in vasculature and also in the brain. And this is also a very active topic of research. We do have collaborations in that sense as well.
Thanks.
Thank you.
Thank you very much, Silvia and Massimo. We have another question from Zara. If you are the possibility to have your question. Thank you very much.
Hi, sorry, I'm outside.
Wow.
Sorry, I didn't want to have my camera on. Just coming back from work. I actually had the same question as Sarah, so thank you very much for responding to her question. That was also my question. But I wanted to ask if actually there is any justification to explore the effects of electrical stimulation in cells that are not known to be electrically active. For example, I know immune cells have shown to be electrically active, but for example, I don't know another type of cell, hepatocytes, for example, in liver. I don't know if your answer would be the same as the answer that you gave to Sarah, but I just wanted to know if there is, for example, if you were about to write a research proposal, what would be your justification when you want to say, I am going to use electrical stimulation for liver cells? Is there like a strong base why it can be very important to also explore that aspect? I turned off my camera.
I have
thank you
to
very
say,
much.
thank you very much. Nice to meet you as well, Zara. Have a good walk. I have to say, I don't know. I think I cannot answer that. I may imagine that maybe, as I mentioned, even low amplitude field across a spectrum may induce some changes, but I'd better ask experts and maybe also collaborators. It would be interesting to try.
Thank you very much. Thank you very much.
Okay, thank you very much again, Massimo. I have only a last question and curiosity about this very interesting work. And what have you tried in your test, in your statistician test, with respect to the microfluidic layer, the possibility to use the capillarity, for example, to avoid the use of electric mechanical pump and other kind of in order to have any mechanical part moving in this platform and the structure at first, and then the last one, the possibility to perform this with this approach also some kind of emulator of three-dimensional structure to grow, for example, cells of part of the human body, in order, for example, to test the efficiency and efficacy of some drugs, for example, during the trial. This is the two short questions.
With respect to the first question, both of them are very interesting. We didn't do that, our cells, but certainly that's an option, and particularly it may require for long-term cells to have a base reservoir of fluid, and certainly the capillary suction has been tested even in paper devices and generally in the, as you know, microfluidic devices. It's certainly a nice option. It would simplify the geometry. It may be particularly relevant for low rates of perfusion, I would say. Another thing that we always, first of all, we had to combat against bubbles, but as always, the elephant in the room. But in particularly in incubator environments, the evaporation is also something to keep an eye on. And so again, I didn't try it directly. I'm generally interested in capillarity. I would wonder what is the precision in which one can with the precision in time of the flow rates. Certainly an interesting point. For the three-dimensional aspect, inherently, I didn't mention splintry, we know there is now ample evidence that only if you indeed develop generally three-dimensional structures, ample evidence that those are going to replicate the phenotype of the tissues better than 2D, for sure. And in general, organ chip is going in that direction. So when we talk about cell cultures are indeed even legacy, by far still well plates are the workhorse for a large part of preclinical tests, for large high throughput screening. The idea is still anyway, wherever possible, to go 3D. And in this sense, the combination of let's call it small chambers with the microfluidics and even stacking of channels and having pillars goes exactly in that direction.
Okay. Thank you very much. So I will thank you again for your contribution to these seminars and for your time also for the question and answer section. So
it's been a pleasure. Thank you very much again, Lucanus, and everybody for the invitation.
Okay, so I thank you again, the speaker, and I remember to everyone that the next seminars will take place at 6th of May, and so we are waiting everyone for the other seminars and the interesting collaboration with Massimo and everyone are interested in our activity, research activity. So thank you again, and have a nice afternoon. Bye. Thanks to everyone. Thanks again.
See you soon.
Bye bye.
Thanks a lot. Bye bye.